Yikes. So, this is Friday, February 12th, 2021. Chemistry CP. I'm going to try to talk students through how to do balancing chemical reactions 1 on the front side as an example of how to do balancing chemical reactions. So, make yourselves comfortable. There are a few rules to follow. For starters, these blank lines in front of the molecules or atoms are the coefficients. All right, my favorite way of having students balance chemical reactions. What does that mean, balancing them? And what does it mean if you're provided a skeleton chemical reaction? A skeleton means you've carefully followed the rules for building a neutral molecule or an atom. So if it's one of the 7 diatomic elements, hydrogen, nitrogen, and so forth, you always wrote it by itself with a subscript 2. If it's any other ionic compound or molecule, you've written it so that it's electrically neutral. So if sodium has a +1 charge and sulfur always has a 2- charge, you have 2 sodiums for every sulfur to make it a neutral molecule. Skeleton means you've correctly written each reactant and each product correctly. So that's a skeleton chemical reaction. Now, a balanced chemical reaction can only be done after the skeleton is correctly done. So if you didn't correctly figure out that zinc sulfide is 1 zinc and 1 sulfur, then no matter what you do next, it's wrong. You can't fix a wrong thing by working on it some more without fixing the wrong part of it. You can't add to something wrong to make it right on this sort of chemistry work. So what I'm going to be guiding you through is balancing, which means whatever you start with in terms of atoms or polyatomic ions, you have to end up with that as well. They can be rearranged, they can be broken apart as to who they're hooked up with, they can be combined. So there's decomposition, there's synthesis, there's exchange that can take place, single displacement, double displacement, there's combustion. In every case, the rule that must be followed is that whatever quantity of one type of substance that you begin with, and substance I mean specifically an atom or a polyatomic ion, you have to end up with that same number total in the products. So here we go. For number 1, I'm going to build a RAP sheet. Yeah, that's what I like to call it. The RAP, the R means for the reactant side of the yield sign. The A means, well, which atom am I talking about? But it really also applies to polyatomic ions. It's just that doesn't, fit the word so well. And then P is for product, meaning everything to the right of the yield sign, all these products, I'm looking at that side of the tally sheet. And so what must be true is that the total number of any atom or polyatomic ion on the left must equal the total number of that same atom or that same polyatomic ion on the right. And when I write my list of which ones I'm looking at, I normally just work left to right across the skeleton equation. So the first element I come across is sodium. The next one is sulfur. The next one is zinc. The next one is bromine. Okay, so there's my entire list. There's nothing on the right that isn't already on the left. There's nothing on the left that isn't on the right. You can't make sodium disappear. You can't make gold appear. You have to have the same substance, same atoms and polyatomic ions on both sides of the yield sign, the reaction. So now I'm going to start tallying them up. The subscript 2 after the sodium means I have 2 sodium atoms on the left. So under reactants, total number of sodiums is 2. Total number of sulfurs in the reactants column is 1. Total number of zincs, 1. Total number of bromines, 2. Now I do exactly the same, it's called bean counting, tallying up on the right side, on the product side. When we look at these blank coefficient placeholders, I remind you we interpret them to be a 1 in front of them until we fix them. Not a 0, but a 1. So I see 1 sodium on the right. I see 1 bromine on the right. I see 1 zinc on the right. I see 1 sulfur on the right. So now I get to study my rap sheet, right? Here's the equation I'm trying to balance. Here's my tally of how many occurrences there are of sodium in the reactant side, how many occurrences there are of the sodium atom on the product side. And I see they don't match. So one of the rules is you can't use half an atom. You can't use half a polyatomic ion. You can't use half of any of these components. So that means you can't use a decimal value here. You can't use a fraction. You are only allowed to use whole numbers. And that means the counting number is actually greater than 0. So 1 is the very lowest choice you have. And then the integers going up from there, 2 or 3 or 4 or 5, and so forth. I see I need more sodiums on the right. I need more bromines on the right. So I'm going to try putting a coefficient of 2. And here's something I do. When I do this rap sheet, I don't use a pen. I use a pencil because it's just a temporary trial and error. I will be content if you guys just do this by trial and error. By trial and error, I'm going to try doubling the sodiums on the right. So I'm going to replace the 1 that's implied there with a 2 in front. And now I'm going to update my rap sheet. 2 sodiums on the right, and also now 2 bromines on the right. Looking at my rap sheet, I see I have 2 sodiums on the left, 2 on the right, 1 sulfur on the left, 1 on the right, 1 zinc on the left, 1 on the right, 2 bromines on the left, 2 on the right. Ta-da! This is now a balanced chemical reaction, and I can write this and state it as 1 molecule of sodium sulfide combines with 1 molecule of zinc bromine to create 2 molecules of sodium bromide plus 1 molecule of zinc sulfide. Ta-da! There's number 1. My goal is to have you become masters of this by the end of the period. So at any point, if you want to leap ahead of me and do the balancing yourself, please beat me to the punchline. I'm now folding my paper over so you can see my rap sheet simultaneously with seeing the equation that we're balancing. So here we go, number 2. On my rap sheet, the R is for the reactant side. A is for what atoms or polyatomic ions, I guess. P for the product side, everything to the right of the arrow. And I build my list just going left to right. So first I see iron, Fe. In parentheses, yeah, you might think that might be carbon, iodine, oxygen, but it's not. That is lowercase letter L. This is chlorine. And it breaks apart. So if I take the trouble and right now I will, if I take the trouble to look up the polyatomic ion named ClO, I see on this list ClO is named hypochlorite. Hypochlorite. Now, if I see ClO to the right of the arrow, then I would say, oh, it stays intact. But I don't see it to the right of the arrow. So this polyatomic ion is going to be broken apart. So I'm going to list it by individual atoms and say, all right, there's chlorine and there's oxygen. There can only be iron, chlorine, and oxygen to the right of the yield sign because you can't destroy the iron, you can't create the iron, you can't destroy gold, you can't create gold. So we're done building our list of atoms. Now I'm going to tally up how many do I see on each side. I see 1 iron on the left in the reactants column. The subscript 3 outside of the parentheses means I multiply everything on the inside by 3. And right now I'm seeing 1 chlorine inside the parentheses with a 3 multiplying that. So I see 3 chlorines on the left. Similarly, I see 3 oxygens on the left. On the right now, altogether, I see a total of 1 iron atom. This subscript 3 only applies to the chlorine because there's no parentheses. So I see 3 chlorines on the right. I see 2 oxygens on the right. Studying my rap sheet, I see, well, ions are good, chlorines are good. Aw, oxygens are not good. What's more, I see the oxygens on the right can only go in multiples of 2, 2, 4, 6, whereas on the left, they can go by odds and evens. I'm going to pause recording because we hit our 3-minute break. Okay, so during my 3-minute break, I discovered it's possible that the audio was not recorded during this class video recording, and that's just sad and too bad. I'm not going to go back because we are so far behind schedule. Trying to just repeat all the rules. So when I do a rap sheet, I make a list of the atoms or polyatomic ions, and then I count how many times they occur total in the reactant side, how many times they occur total in the product side, and then I strive to make them equal. I can only multiply, increase the coefficients into higher valued whole numbers. So as I look at this, I see I need more oxygens on the right, and on the left, I can only go in multiples of 3. So I am going to guess that I need to triple the amount of oxygens on the right. That will give me 6 oxygens on the right. To match that, I'm going to double the number of oxygens on the left, but I have to update all of these atoms. So now I have 2 irons on the left. Now I have 3 times 2 is 6 chlorines on the left. And now I have 2 times 3 is 6 oxygens on the left. So the oxygens now agree, nothing else now agrees. My next attempt to fix things is to double the number of irons on the right. Updating my records, that means I now have 2 irons on the right. I now have 2 times 3 is 6 chlorines on the right. Looking at my updated rap sheet, I see this is balanced. 2 iron chlorates decomposed into 2 iron 3 chlorides. And by the way, I should use a Roman numeral here too. So 2 iron 3 chlorides, chlorates, whatever that is, hypochlorites. 2 iron 3 hypochlorites decompose into 2 iron 3 chlorides plus 3 oxygen molecules. All right, beat me. Go do the next one before I do. Meanwhile, I'll just keep going along, narrating as I go, trying to finish this up with time to spare if at all possible. On number 3, my rap sheet, the reactant side, the atoms or polyatomic atoms, molecules, product side, there's my rap sheet. I see I'm dealing with nitrogen and hydrogen. On the left, I see I have 2 nitrogens and 2 hydrogens. On the right, I see I have 1 nitrogen and 3 hydrogens. How interesting. The hydrogens can only go in multiples of 3. So I can start off with a coefficient of 2 in front of these ammonia molecules. That means I now have 2 nitrogens on the right, and 2 times 3 is 6 hydrogens on the right. To fix that, I need to triple the number of hydrogens on the left. So I'm going to bump the coefficient in front of the H2 up to a 3 from a 1. That means I now have 6 hydrogens on the left. I currently have two nitrogens on the left, 2 on the right, and it is all balanced. So we would say I have 1 molecule of nitrogen gas combines with 3 molecules of hydrogen gas to form 2 molecules of ammonia. All right, do the next one. Beat me. And if you're playing this video afterwards, pause it now, solve it, and then play the video to see what I come up with. Number 4. On this rap sheet, I see I have an ammonium polyatomic ion that does not break apart. It's still an ammonium polyatomic ion in the products. So there's no reason to break it into individual atoms of nitrogen and hydrogen. I can treat it as the group that it is, NH4. Same thing can be said for arsenate. I see ASO4 on the left. I see it still as a group on the right. There's no arsenic anywhere else. There's no oxygen anywhere else. So I can treat this as a complete group, ASO4. On the left, I see I have the element barium. And CN is also a polyatomic ion. I see it stays together as a group on the right. CN is called cyanide. This completes my list. I don't need to break it into individual atoms. I can leave these as polyatomic ions that I'm dealing with. All right, so on the left, the 3 outside the parentheses means I have 3 ammonium polyatomic ions. No parentheses for the arsenate, so I have just one of those. 1 barium, because that 2 is only talking about the parentheses. So I have 1 barium, 2 cyanides. I was going to check one more thing since I used the term, and the short answer is I've misplaced the reference sheet, so I'm just assuming that's arsenate. I might have the wrong name. On the right, I count up, I have 1 ammonium, 1 cyanide, 3 bariums, 2 arsenates. 'Tis not balanced, so I need to balance it. I can only increase the coefficients above the ones that we start off with. How about if I triple the ammoniums for starters? So on the product side, how about if I try 3 ammoniums? Updating my rap sheet, that means I now have 3 ammoniums on the right, and I have 3 cyanides on the right as well. Okay, so that doesn't look so good because the cyanides are going by multiples of 3, which are odd numbers. On the left, they're going by multiples of 2, always, which are even numbers. So right away, I see this isn't going to work. I should find myself an eraser. And upgrade my guess. Instead of putting a 3 there, I'm going to double it and put a 6. So now my rap sheet says I have 6 ammoniums on the right and 6 cyanides on the right. Okay, well, Now I'm going to tackle, let's say, the ammoniums on the left. I have 6 ammoniums on the right, only 3 on the left, so I'm going to double the ammoniums on the left and update my rap sheet. So 2 times 3 is 6 on the left. 2 times 1 group is 2 on the left for the arsenates. Well, alrighty. The bariums aren't balanced. I have 3 of them on the right. I only have 1 of them on the left. So how about if I triple the ones on the left? There is my guess. Updating my rap sheet, I now have 3 bariums on the left, and 3 times 2 is 6 cyanides on the left. I look at my updated rap sheet, everything balances. So the answer is 2 molecules of ammonium arsenate combine with 3 molecules of barium cyanide to produce 6 molecules of ammonium cyanide plus 1 molecule of barium arsenate. All right, do the next one. Beat me to the answer. Number 5. I see I have silver, phosphorus, aluminum, and chlorine. All right. I have 3 silvers on the reactant side, 1 phosphorus, 1 aluminum, and 3 chlorines. On the product side, I see I have 1 silver, 1 chlorine, 1 aluminum, and 1 phosphorus. Well, it's not balanced. Go to work. I will guess tripling the silvers on the right. So I'm going to up the coefficient from an implied 1 to a 3 and update my rap sheet in front of the. So now I have 3 silvers on the right. I have 3 chlorines on the right. Looking at my updated rap sheet, I'm done. So the solution for number 5, the balanced chemical reaction is 1 molecule of silver phosphide combines with 1 molecule of aluminum chloride to produce 3 molecules of silver chloride plus 1 molecule of aluminum phosphide. All right, do number 6. Number 6, I see I have lead, which is Pb. NO3 continues as a group on both left and right. I just found my reference sheets, and I can look up NO3 in case I forgot the name, and it's called nitrate. And while I'm at it, ASO4 is called arsenate. I'm not sure I referred to it correctly. So ASO4 was arsenate, NO3 is nitrate. Alrighty. So it stays together as a group. I can just write it as a group, NO3. Mg, magnesium, O for oxygen. All right, now let's tally them up. On the left, on the reactant side, I see I have 1 lead atom. I have 4 nitrate polyatomic ions. I have 1 magnesium atom and 1 oxygen atom. On the product side, I see I have 1 lead atom, 2 oxygen atoms, because I'm not going to count the oxygens in the polyatomic ion. I'm only going to count the polyatomic ion as a group. I did the same thing on the left, by the way. Otherwise, I'd say, what would I have here? 3 times 4. I actually have 13 oxygen atoms in my reactant pile. 12 of them are here in the nitrate, and 1 was in the magnesium oxide. It's much easier to leave the groups as groups if they stay as groups. So anyways, on the product side, I see I have 2 nitrates. 1 magnesium and 2 oxygens. Studying my rap sheet, the general philosophy is anytime oxygen is by itself, such as in a combustion reaction, balance it last. Okay, keep that in mind for future reference. For now, I'm going to try doubling the nitrates on the right. So doubling the nitrates on the right. Updating my records, that gives me 2 magnesiums on the right, not just 1. And 2 times 2 is 4 nitrates on the right. That might be progress. Now I see I need more magnesiums on the left, so I'm going to double them. Coefficient goes from 1 to 2 for the magnesium oxide. Updating my rap sheet, I now have 2 magnesiums on the left and 2 oxygens on the left as well that are part of that magnesium oxide, ignoring the oxygens that are in the lead 4 nitrate. My rap sheet is now balanced, and I can declare this as being 1 molecule of lead, but lead has multiple oxidation states. Which one is this? Lead Roman numeral 1, 2, 3, or 4? Well, nitrate, you probably don't remember, is a 1 minus charged polyatomic ion. If I need 4 of them to electrically neutralize this 1 lead atom or ion, this lead must be Roman numeral 4. So as a sentence, I would say 1 molecule of lead 4 nitrate combines with 2 molecules of magnesium oxide to produce 1 molecule. And by the way, don't get confused here. This says PbO2, but every oxygen is always a 2 minus charge. And I need 2 of them. So this lead must be a 4 plus charge as well, just like it was earlier. So even though there's a subscript 2 here, we would say this is lead 4 oxide. So combine to produce 1 molecule of lead 4 oxide plus 2 molecules of magnesium nitrate. Ta-da! Do number 7 before I do. Ah, yes, this guy has a rap sheet a mile long. All right, so I begin by recognizing that NH4 is the ammonium polyatomic anion, and that it stays together as a group in the products. So I'm going to list it as the group NH4. MnO4 is another polyatomic ion. When we look it up, MnO4, oh, where? There you are. Okay, so MnO4 is called permanganate. Permanganate, and it's a group. It stays together as a permanganate over on the products. So MnO4, the group chromium, and SO4, that one you should kind of recognize is sulfate, another polyatomic ion that remains as a group. Now, tally up how many I have of each. On the reactant side, I see I have 1 ammonium, 1 permanganate, 2 chromiums, and 3 sulfates. On the product side, I have 2 ammoniums, 1 sulfate, 1 chromium, and 3 permanganates. There's my rap sheet. Now, balance it. Thinking about it, I'm going to want to end up with 3 sulfates on the right for every 1 on the left. The ammoniums go by 2s on the right. The permanganates go by 3s on the right. So, wild guess, you can start anywhere and just do it trial and error. If I were to triple the ammonium sulfates on the right, I think I can make it go forward from there. So I'm going to put a 3 in front of the ammonium sulfates. And on the right, that means I have 3 times 2 is 6 ammoniums on the right now. 3 sulfates on the right. How about if I increase the ammoniums on the left by a factor of 6? Wow. So 6 is my new coefficient for the ammonium permanganate. Updating my rap sheet, I now have 6 ammoniums on the left and 6 permanganates on the left. I need more permanganates on the right. I need to double them. So I'm going to change the coefficient from 1 to 2 on the chromium 3 permanganate. The chromium is a polyatomic cation, so you have to use the Roman numerals for which one you have. Updating my records on the right, I now have 2 chromiums on the right, and 2 times 3 is 6 permanganates on the right. Looking at my updated rap sheet, everything now balances. I'm done balancing it. I would say 6 molecules of ammonium permanganate combined with 1 molecule of chromium 3 sulfate to produce 3 molecules of ammonium sulfate and 2 molecules of chromium 3 permanganate. Do number 8 before I do. Technical difficulties. Nice. Number 8 is a decomposition reaction. As I build up my rap sheet, I see I have chlorine that breaks apart, so I do have to do it by the individual atoms, oxygens, and that's it. All right, on the left, I see I have 2 chlorines, 7 oxygens. On the right, I have 2 chlorines and 2 oxygens. Oh my goodness. The oxygens on the left can only increase in multiples of 7. I'll try doubling them. All right, so now 2 times 2 means I have 4 chlorines on the left. 2 times 7 means I now have 14 oxygens on the reactant side. On the product side, I need twice as many chlorines as I have. So I'm going to increase the coefficient from 1 to 2. Updating my rap sheet, 2 times 2 is 4 chlorines on the right. Now I need 14 oxygens on the right. Very conveniently, try 7 as the coefficient. 7 times 2 gives me 14 oxygens on the right. This is now a balanced chemical reaction, stating 2 molecules of dichloride septoxide decompose into 2 molecules of chlorine gas and 7 molecules of oxygen gas. We just take it for granted that chlorine and oxygen are going to be in the gaseous state at standard temperature and pressure, which is where we do chemical reactions, unless we specify otherwise. All right, beat me. Do number 9 before I do. My rap sheet for number 9, copper. Cr2O7 is a polyatomic ion. I could look up its name and see it's called dichromate. Cr2O7 with the 2- charge is called dichromate. And it stays together as a group. So I can leave it as Cr2O7, the group. Calcium and nitrogen. There is my list of atoms or polyatomic ions. Counting them up on the reactant side, I have 1 copper, 1 dichromate, 3 calciums, 2 nitrogens. On the product side, I see I have 3 coppers. Woo! How many robbers? I don't know. 2 nitrogens, 1 calcium, and 1 dichromate. All right, you guys are experts at this. I should say nothing, and you should figure out the answer. Ta-da! And copper is multiple cation. So I have to declare which oxidation number it is using Roman numerals. Dichromate was a 2-. So this is copper. There's 3 molecules, or ionic compounds, perhaps, of copper 2 dichromate combined with 1 molecule of calcium nitride to produce 1 molecule of copper 2 nitride plus 3 molecules of calcium dichromate. Last one. This is called a combustion reaction. C3H8O is a hydrocarbon, and it decomposes, it burns in the presence of oxygen. So we're going to have to go individual atoms: carbon, hydrogen, and oxygen. Okay. Yikes. On the left, we have 3 carbons, 8 hydrogens, 1 oxygen here, plus 2 more over there. I almost wonder if I should consider it that way, but no, I think I would just say I have 3 oxygens. Maybe I should count the O's and the O2s separately. Interesting idea. Not going to do it. So I have 3 oxygens on the left. And by the way, you try this. It might work better for you. I'm just going to do things foolishly. On the product side, I see I have 1 carbon, 1, 2, 3 oxygens, and 2 hydrogens. Do you remember the advice I said when the microphone wasn't recording it? I said, when you have a combustion reaction, balance the oxygens last. I think that's the rule. It's either the oxygens or the waters. I think you just keep adding water to make it balanced, and then you add the oxygens to finish it off. So let's try this. I need 3 times as much carbon on the right. I need 4 times as much hydrogen on the right. And it looks as if the oxygens are good, but that's not going to stay that way. So I'm going to tackle the carbons first, because definitely, there's no other way of dealing with the carbons. It's a 3-to-1 ratio all the time. So let me try 3 carbons on the right. Updating my rap sheet, I have 3 carbons. Now I have 6 plus 1. Now I have 7 oxygens on the right. Yikes. Let me try to fix the hydrogens. On the left, I have 8. On the right, I only have 2. Let me goose that up and try a coefficient of 4 in front of the water. Updating my rap sheet, this means I now have 8 hydrogens on the right. And total, look, I have 3 times 2 is 6, plus 4 times 1 is a total of 10 oxygens on the right. Crazy. Now, I can already tell you I'm going to have to go higher with everything because well, just because. Okay, if I try to increase the oxygens right now, I'm going to still end up with an odd number because it's 1 plus an even number is an odd number. So 2, 4, 6, 8 plus 1 just doesn't get me to 10. I'm going to try doubling this molecule on the left. Wow, so now I have 6 carbons on the left. I have 16 hydrogens on the left. I have 2 plus 2, I have 4 oxygens on the left. Fixing the carbons, I'm going to double the carbon dioxide from 3 to 6. So now I have 6 carbons on the right. 6 times 2 is 12. 12 plus 4 is 16 total oxygens on the right. Well, the hydrogens don't match. I have 16 hydrogens on the left and only 8 on the right. So I'm going to double the hydrogens on the right. And by the way, I feel like I'm going in the right direction. So 8 times 2 is 16 hydrogens and 8 oxygens plus 12 oxygens. 6 times 2 is 12 plus 8 is 20. I now have 20 oxygens on the right, but I feel good about that because here's my source of as much oxygen as I need to make this work out. I need a total of 20 on the right. I have 2 already in use on the left. So 20 minus 2 is 18. 18 divided by 2 is 9. Now I have a total of 20 oxygens on the left, 20 on the right. This concludes my recording. This concludes